Hello everyone. The May 2025 papers have just been unofficially released quite early this year, only about 1 week after the exams. In this video, I will analyze the AAHL only question from the time zone A paper 1. I have already made a video on the SL paper which contains some of the HL questions, and I will include the link to the SL video in the video description of the current video. So without further ado, let's jump into question 6, which is the first HL only question about some vector 3D lines intersecting at right angles. So to ensure that the lines intersect at right angles, we need to ensure that the dot product of the direction vector equal to 0. Because the dot product equaling to 0 means that cos angle equal to 0, which further means that the angle is 90. So reading off the components of the direction vector, we have 0, A1 from the first line and 1, 2, 3 for the second line. Setting the dot product equal to 0, we have 2a plus 3 equal to 0, leading to a equals to negative 3 over 2. Now we move on to ensuring that the lines intersect. So for two lines in 3D to intersect, we need to make sure that the same lambda and same mu can allow, well, the lambda and mu can allow all three components to equal to each other. So we set up the vector line equations, reading off the components carefully. We have 4, 0, negative 1 plus 0 lambda, a lambda. And actually we have already found a, so let's just put in the value in 3 over 2 lambda. And then plus just 1 lambda, which needs to equal to 1, 0 b, actually negative b, plus mu, 2 mu, and 3 mu. In the worst case scenario, we will get 3 equations and 3 unknowns, which we can solve simultaneously. Fortunately for this question, I think the first component already allows us to determine that mu equals to 3. We can now use mu equals to 3 in the second component. And this gives lambda equals to negative 4, I think. And finally, we can use these two values of lambda and mu to deduce the value of b, which is 14. So relatively uneventful question 6. Question 7 is about some complex numbers. So writing 3 in the form of e to the a, so we have 3 equals to e to the a, so clearly a equals to ln 3. So 3 can be written as e to the ln 3. So using this result for parts b, well, z equals to 3 to the I minus 1, and what I would like to do is to first isolate the minus 1. I would skip that. This is 3 to the I times 3 to the negative 1, which equals to 1/3 times 3 to the I. And using the result from above, we have 1/3 times e to the ln 3 times I, according to exponent laws. And we can now convert this Euler form into Gauss's argument form, cos ln 3 plus I sine ln 3. The I is a little bit ugly. And clearly the real part of z is just 1/3 cos ln 3. The second part now, real part of the reciprocal of the original complex number. We'll take a reciprocal is equivalent to power negative 1. So we're going to make the power the negative of the previous version. So we now have real part of 3 times 3 to the negative I. E to the ln 3 times negative I, which I'll write like this. And then now convert this into cis theta form. 3 cos negative ln 3 plus I sine negative ln 3. So the real part, which is equal to 3 cos negative ln 3. And using log rules allows us to write negative ln 3 as ln of 3 to the negative 1. Which equals 3 cos ln 1/3. But this kind of question I don't remember seeing before from past papers. And that may have thrown some people off. And the general consensus apparently for this year is that the papers are hard. But we already know that the SL, actually everyone has had a partition. And it actually worked in 2016 when the new physics syllabus at the time led to a very difficult paper. And then the physics grade boundary has been lowered by about 10%. So it was a successful partition about 10 years ago. Question 8 now, some induction question involving inequalities. Well, let's address the proof in part A first. So left-hand side equals to 1 plus log 2n, so nothing new, just copying the original. Because the target right-hand side is in the form of a single log, it's probably a good idea to rewrite the 1 as log 2, and the log rule allows us to turn log plus log into a product. And we now have to justify that 2n is bigger than n plus 1. And I think the best way to continue is just to rewrite 2n as n plus n. And now we can bring in the inequality because under the restriction that n is a positive whole number, n is greater than 1 for sure, and log is order preserving. The bigger the number, the bigger the log of the number as well. So part B, using mathematical induction to prove the original statement, n bigger than log to the base 2 of n. So standard format for constructing an induction proof. Let Pn be the original proposition. So lots of writing, but you can't skip this. So test n equals to 1. The left-hand side is 1. And then right-hand side is 0. 1 bigger than, actually strictly bigger than 0. Therefore, P1 is true. We now assume that Pn is true for some n equals to k. So k is bigger than log to the base 2 of k. We want to show Pn is true for n equals to k plus 1. So we are just writing out the target statement without claiming that we have proven it. The left-hand side of P k plus 1 was simply equal to k plus 1 alone. And the assumptions say that k itself is bigger than log 2k. And then we can further justify that this has to be bigger than log 2 of k plus 1 by the result in part A. So the induction proof inductive set has very, very few steps in this for this particular question, because most of the algebra has already been covered under part A. And then just write the concluding statements. By the principle of MI. P n is true for all positive whole numbers n. Next question, question 9 is about solving a homogeneous differential equation. I hope you guys are aware of the standard move for solving this. So you want to let y equals to v times x, where v itself is a function of x. So dy over dx can be shown using product rule and implicit differentiation to be x plus v d, whoops, it should be v plus x, my bad, v plus x dv over dx. So replacing all the y's with v's, we now have v plus x dv over dx equals to x plus x minus vx, my bad, all over x plus, I said vx, I wrote xv, of course they're the same. The right hand side simplifies somewhat because the x's are gone. 1 minus v, 1 plus v. And then now we will try to turn this into a separated, like a separable, well, this is supposed to be a separable variable, separable differential equation in terms of x and v. Just getting a common denominator. We'll clean up the top a little bit first. Cross multiply divide. At this stage, some people may want to use, actually I missed my dv. It looks like you may be able to use partial fraction on the left-hand side, except that the denominator is not nicely factorizable. It has some irrational roots. If you have good eyes, which you actually need good eyes here, you should be able to spot that you can make a substitution. If we just let u to be the denominator, you realize that du over dv is minus 2v minus 2, which is a constant multiple of the numerator. So making the substitution, we still have 1 plus v at the top, u at the bottom. dv now becomes du over minus 2. I'll just factorize out the minus 2, and you realize that the v plus 1 is about to get cancelled. So we are looking at minus 1 over 2, 1 over u equals to 1 over x. With the du equals to 1 over x dx. So minus 1 over 2 ln u equals to ln x plus c. And let's bring back the v. Minus v squared minus 2v plus 1 equals to ln x plus c. Using the initial condition, y equals to 0 when x equals to 2, which also implies that v itself has to equal to 0. So we have minus half ln 1 equals to ln 2 plus c. And since ln 1 is 0, c is minus ln 2. So minus half ln minus v squared minus 2v plus 1 equal to ln x minus ln 2, I'm going to rewrite as ln x over 2. I'm going to multiply both sides by negative 2 and then move the power into the x over 2. And with the negative power, we will end up flipping the, I'll just write this as 4 over x squared. I probably don't need an absolute sign anymore, but I'll keep it there for one more step. And then get rid of the natural logs. And then back substitute v as y over x. And then multiply by x squared throughout. Oops, I made a sign mistake. And that's exactly what they have. So there are a lot of steps, there are a lot of log rules, and there are a lot of standard moves that you need to be familiar with, but overall, I would say it's manageable. It's hard, but manageable. Question 10 is supposedly common with ESA, but the last part, finding the domain of a composite. Let's just do it anyways. So G of F is just going to be natural log of the quadratic. And finding the domain of such composite is basically an inequality problem because the content of the natural log needs to be positive. And this is a standard positive quadratic inequality. If we just construct a quick sign diagram, you realize that we need x to be more negative than -3 or x is bigger than -1. Moving on, question 11 has two parts. The first part is a legitimate vector problem. For the first part, you need to find the angle between two planes. And in my opinion, I think 6 marks is a little bit too much for this kind of question. Because when you have two planes, so let's say I'm looking down a line, the line of intersection of the two planes. So these two green arrows are the normal vectors. You can use a whole bunch of angle geometry to justify why this angle equals to this angle, and this obtuse angle equal to this other obtuse angle. So you're basically trying to find the angle between the normal vectors, which can be achieved by just taking the dot product. So the dot product of the normal vector, you can simply read off the x, y, and z components. So 1, 2, 1, dot 1 minus 1 minus 2 equals to the magnitude of the two normal vectors and cos of an angle. I think in this case, the dot product is negative. It's 1 minus 2 minus 2 equals to root 6 cos angle. So I'll just mark theta to be the obtuse angle. So minus 3 equals to 6 cos theta. Minus 1 over 2 equals to cos theta. So if you're familiar with exact values, and all HR students should, so theta just equal to 120. And then the acute angle, which is equal to 180 minus the answer, which is 60 degrees. Now, part B, we have a third plane that is perpendicular to both original planes. And they give us the original point of intersection. So for this kind of question, there are two planes that go like this. What you need to realize is that the direction vector of the line of intersection of the first two planes will serve as a normal vector for the third plane. And because we know a point that lies on the third plane, we can eventually use A dot n equals to R dot n, which is in the formula book. We first need to find the n, and the n is going to be the cross product of the two normal vectors. And personally, I'd like to use the determinant approach. Mistakes were made. To find the cross product. Approach is specify 1, 2, 1, cross 1, negative 1, negative 2, equal to this determinant approach. It turns out if you multiply this out, you get minus 3i plus 3j minus 3k. And you can scale down this normal vector. So n3 can therefore be -1, +1, -1. And then we can now use A dot n equals to R dot n. So we have 5, -5, 5, dot -1, 1, -1 equals to R, which is just your standard x, y, z, dot -1, 1, -1. And when you expand all this, you get minus x plus y minus n equals to negative 15, which would be the Cartesian equation. The third part looks difficult, but then if you read more carefully, using an appropriate method, using an appropriate compound angle identity to justify sine 75 as this exact value. And turns out this is just a sine root problem. So sine 75 can be written as sine 40 plus 30, 45 plus 30. 120 minus 45 also works, but I think adding two smaller angles is more straightforward. So using the sine compound angle identity, which I hope you guys have memorized, even though it is in the formula book, I'll use root 2 over 2 because the surds should be at the top. Possibility is this. And this gives you root 6 plus root 2 all over 4 as needed. And then to find QR, again, it should just be a matter of using sine rule. So QR over sine 45 equals to PR, which is 5, over sine Q. So QR simply equals to 5 sine 45 over sine 75. So now let's use the exact surd forms. So 5 times root 2 all over 2 divided by sine 75 is the same as multiplying by the reciprocal of sine 75. We know some of the numbers. Actually, the 5 does not cancel, but I'll just write 10 root 2 over root 6 plus root 2. And all you need to do is to do some grade 10 rationalization. The top becomes 10 root 12 minus 20. The bottom becomes a 4. Root 12 itself is 2 root 3, so we have 20 root 3 minus 20 all over 4. And you can factorize out of 5. So that should be the correct answer, I hope. Last question. Question 12 is the most challenging question, I think. There's a lot of integration. Integration by parts, but they do guide you through a little bit, but there are some unfamiliar techniques that need students to have some good general awareness. We'll do parts A, B, and C first. I need to scroll a little bit. So part A, cos to the power of n x dx. So if you just let u to be cos n minus 1x, should we let u to be cos x, or should we let u to be cos n minus 1x? I think it should be very clear that u should be this cos x raised to some ugly power, because this thing cannot be easily integrated. Whereas if we just let dv over dx equal to cos x, then v can be neatly integrated, becomes sine x. du over dx, meanwhile, can be found using a combination of power and chain rule. N minus 1 cos n minus 2 x times negative sine x. So using integration by parts, u dv when integrated becomes uv. So we have cos n minus 1 x sine x minus the integral of v du minus sine x dx. The front is already set in stone. Now, student would have to figure out how to rewrite the back part in a way that's the same as this. So the n minus 1 seems to be in place. There's no sine square anymore in the final form, so most likely we have to use sine square plus cos square. equals to 1 somewhere. We can move this n minus 1 outside the integral first, I think. Cos n minus 2x. So cos square x plus sine square x equals to 1. We can show that negative sine square x equals to cos square x minus 1. And I deliberately include a negative on the right hand side, because I can now replace negative sine square x as cos square x minus 1. And I can split the integrals. Well, I can expand it first. So cos n minus 2x times cos x. Cos square x is just cos to the nx minus cos n minus 2 x dx. And when you split the integral, taking into account the double minus, I think you just get the target statement. You see the double minus leading to a plus minus n minus 1 cos nx dx. So that should be it for part A. Now, second part, hence show that f nx, the cos to raise to some nth unknown nth power equal to some weird looking expression. But what you can do is to realize that this f nx is somewhere not only on the left hand side, but also on the right hand side. And meanwhile, this other integral can be represented as f n minus 2x as well. So let's just re-summarize the original. F nx dx equals, so we still have the cos n minus 1x sine x plus bracket n minus 1 f n minus 2 x, and Mr. dx here, minus n minus 1 f n x dx. And you can now move this term to the left hand side. So we have f n x, and I'll factorize it out as well, because I have a 1 from the original left hand side, plus n minus 1, which is this n minus 1, equals to dx equals to everything else unchanged at this point, I believe. One plus n minus 1 is just n. And then this n, which is the constant, can be divided onto the right side. And once I do that, the right side looks exactly like this. And I'm not going to bother to rewrite this. There's only 2 marks. And the part C, hence find an expression for cos to the 4. And clearly we have to use n equals to 4. So we have cos to the 4x dx would equal to 1 over 4 cos cube x sine x, using the result in part B, plus 3 over 4 times the integral of n minus 2 is 2, so cos square x dx. And HR students should know how to integrate cos square x. We do so by using the double angle formula. Cos 2x equal to 2 cos square x minus 1, so cos 2x plus 1 all over 2 equals to cos square x. You further integrate, it's cos cube x by that. I actually made a similar mistake in the SL paper. It's quite annoying that I made a lot of. I've discovered a couple of mistakes in my SL video, but I really don't have the time. I'm not really a full-time YouTuber. Instead, I'll just allude to my mistake in the video comment and hope you guys understand and to appreciate my effort. Integrating cos 2x plus 1 all over 2 gives you a quarter sine 2x plus half x plus c, and if I group some of the terms, if you compare our current result with the target, we have that. Okay. They have cos x sine x, we have sine 2x, and this is clearly just an application of the sine double angle formula. We'll have 3 over 16, but then we have a 2 coming out from sine 2x. So 3 over 8 sine x cos x plus half x plus c. So we can claim that P equals to a quarter, and Q equals to 3 over 8, and R equals a half. So that should be it for part C. Part D now. On the volume of a solid of revolution. Let's recall the result from the previous part. So the integral of cos to the 4x equals to quarter cos cube x sine x plus 3 over 8. I think I made a mistake, but it should be 3 over 8 sine x cos x. And then there should be another 3 over 8. Yeah, it was a mistake. I think I wrote R to be 1/2. I need to multiply the 1/2 by 3/4 as well. So we have this result in mind, so we can now find the volume of revolution of the solid by first setting up the integral. So it's pi fx all squared dx with the boundary of negative pi over 2 to the positive pi over 2. So when you square fx being cos square x, it's just a pi cos to the 4 x dx. And basically, we can just use the integration result from above. Cos cube x sine x plus 3 over x sine x cos x plus 3 over 8 x upper bound, lower bound. And realizing that cos pi over 2 and cos negative pi over 2 are both 0. The trig terms all disappear, and we now have 3 over 8 times pi over 2 minus 3 over 8 times minus pi over 2, leading to 3 over 8 pi squared. Cubic cube, which is what C and Q. And then part E, last part in the Maclaurin series. So find the Maclaurin series of f and x after the term in x squared. So cos nx just equals to cos x to the n. And the cos x series is available in the formula book, but I hope you guys have seen enough of it. There are higher power terms, but because they only want us to expand up to x squared, I think this should be suffice. This should be sufficient. Using the general binomial expansion, we will now have 1 minus n over 2 x squared plus higher power terms. And then to find the limit of n x minus 1 all over x, where we just replace the series we'll apply the series expansion result from above. The ones are gone, and then the x squares are gone. And the final answer is negative n/2. And I think I've tracked this answer on decimals. It should be correct. So that would be it for this entire paper. I hope you guys find the techniques useful, and I will hope to have time to comment on the other timezone papers. See you guys in a new video. Thank you for watching.